All right, it's Sharpie. I can't erase it.
Erase it. Oh.
Quit it.
Awkward.
Okay, so work. Giving and taking energy by force. Can everybody see?
Oh, there's a lot.
Okay, so one way that we can do work is by lifting things. Now, the old equation that you remember from before was work equals, how does it go again? Starts with, now 1/2 mv squared, that's a different one. Work equals force times, yeah, force times, well, displacement actually, times, there's one more thing, cos theta, yeah. Cos theta. And people that have taken the calculus course, anybody recognize what type of vector multiplication that is? Dot product? Are you sure? Yeah, it is. Yeah, it's dot product. Okay. All right. Work equals force times displacement times cosine of theta. Now, if you're lifting, let's draw a picture of lifting. If you're lifting, we can just draw a free body diagram. We know that the force applied is going to be upwards, and the force due to gravity may be downwards. But if we want to know the lifting work done by a lifter, what direction is the applied force? Yeah, it's up. What direction is the displacement if you lift something? Yeah, if it's being lifted, we've got a delta D that's also up. So in that case, what's the angle between the applied force and the displacement? 0. Yeah, big goose egg. Okay, so I mean, really, if you want to see why that's 0, one's going up, the other one's going up. They're basically collinear. No angle between those two vectors. So we'd say that theta is equal to 0. What's cosine of 0 when I sub that in right here?
1.
Yeah, cosine of 0 is 1. So we know that in this case, that part of the equation is going to reduce down to just being 1. Let's say that we have an object that has a mass of 10 kilograms. 10 kilograms. What's the force due to gravity? Yeah, 98.1 newtons. Assuming gravity is 9.81 meters per second squared. So 98.1 newtons downwards. What's the applied force that's going to be required to lift such a thing? Yeah, 98.1 newtons, if you're going to lift it at a constant rate. 98.1 newtons. Oh, did I? I put a point but no 1. Oh, you're right. All right, so if I start subbing in values, my force applied in this case for the amount of work a lifter would do would be 98.1 newtons times delta D, which is, oh, we don't have a displacement yet. Let's figure out how much work it would do. What's a good height to lift something? 1 meter. 1 meter, okay. Lazy mathematician. All right, 1 meter.
What about 1.5 meters?
All right, 1 has already been voted upon. All right, 1.0 meters. And then cosine of 0 would just reduce to 1, so we'll leave it. And now we get 98.1 times 1 meter, which,
98.1 joules.
well, let's not get ahead of ourselves. 98.1 Newton meters is what it shows up as being the obvious unit here. But somebody says that's the same as saying joules. So Newton meters are the same thing as saying joules. If I break down this whole Newton meter thing down into truly it's composite units. Let's say, look, I know that newtons are kilogram meters per second squared. That's something I know from previously. Because really, remember, F equals ma, kilograms times meter per second squared. I mean, we have some source for where these units came from. And we still have meters. So if I wanted to rewrite joules as all the base units together, how would I rewrite it? Yeah. Yeah, kilogram meter squared per second squared. So if you see Newton meters, if you see kilogram meters squared per second squared, or if you see joules, those guys are all equivalent units. Okay, and it all works out to being the same thing by definition. Any questions about that? The work to lift something by 1 meter.